In this video, I'll be talking about the general properties of electromagnetic radiation, or light. The first half of this course is based on techniques that probe the interaction of matter with electromagnetic radiation. These are known as spectroscopic techniques, or generally spectroscopy. So electromagnetic radiation consists of an orthogonal electric and magnetic field, so electric and magnetic, that mutually support each other, allowing propagation even in the absence of a material, for example, in a vacuum. So here you can see that the electric field, which is a vector, is plane polarized along the y direction. And this just means that oscillations of this field lie in a single plane. Now, the magnetic field, which is always orthogonal or perpendicular to the electric field, lies along the z direction in this case. And this entire wave is propagating along x. And we usually refer to this entire vector as the k, or wave vector. Often, only the electric field component is shown, just because the magnetic field interactions with matter are very weak. So if we're looking here in the figure B at the electric field component of the radiation, the amplitude of the wave is given by the length of the electric field vector at the wave maximum. So this distance here, whereas the wavelength is the distance between successive maxima. The frequency of the wave, which is denoted with the Greek letter nu, is the number of oscillations per second. So if we chose a point along this axis, it would be the number of times that wave passed that point in 1 second. The velocity of propagation for this wave is given by vi, and the subscript I here just indicates that the wavelength depends on the medium that the wave is propagating through, and it's equal to the frequency times the wavelength. And so the frequency has units of cycles per second. The wavelength is in meters per cycle. And this means that the velocity has units of meters per second. In a vacuum, waves travel at their maximum velocity. And this is given by c. And it's related to the frequency and the wavelength, with the subscript 0 indicating that it's in a vacuum. And this is approximately equal to 300 million meters per second. Now, in any medium that actually contains matter, so other than a vacuum, wave propagation is slowed by interaction between the electromagnetic field of the radiation and the electrons in the matter. So, for example, here, going from a medium of air to glass, you can see that the wave propagating through the air has a wavelength of 500 nanometers. However, once it reaches glass, which is much more dense than air and has a different refractive index, we see that the wavelength decreases quite significantly. And this is just because it takes time for those two electric fields, that of the wave and that of from the electrons in the matter, it takes time for them to interact, and so it slows down. However, when it again reaches air, the wavelength is recovered. So since the frequency is invariant, it must be the wavelength that decreases. And this decreases according to this expression here, where again this subscript 0 is indicating the wavelength in a vacuum. So to give the mathematical description of a wave, the above wave that we were just looking at can be described by this equation here, where y is the magnitude of the electric field vector at some time t, a is the amplitude, and omega here is the angular velocity, and phi is the phase angle. Now the angular velocity is related to the frequency of the radiation through the following equation, where this is the frequency. And if we sub this equation into equation 1, what we end up with is now this phase angle here, or phase difference, arises when one wave vector leads or lags a second by this amount, the phase angle. So if two waves are traversing the same space, the two waves can add together according to their frequency, amplitude, and phase angle. And this leads to either constructive or destructive interference. So in order to achieve the maximum constructive interference, the two waves, or the phase difference between the two waves, 1 and 2, have to be equal to either 0 degrees, 360 degrees, or some integer multiple of 360 degrees. And if we write this in radians, it can be also expressed as 2 pi or n2 pi. Now for maximum destructive interference, the phase difference between those two waves has to be instead equal to 180 or 180 degrees plus some integer multiple of 360. And again, this can be written as pi or now when two waves have a sharply defined phase difference or phase angle that remains constant with time, they are said to be coherent. So the conditions for coherence are that the two waves must have identical frequencies, and they must also have a constant phase relationship. Now, refractive index, which I mentioned earlier, is one measure of a material's interaction with radiation, and it can be defined as this, where again this subscript I is indicating that it's dependent on the medium, and C is the velocity of the wave in a vacuum, whereas the V with subscript I is the velocity in the medium. And now the refractive index, N, varies. We know that it varies with the wavelength, and it varies according to this equation, which is a fairly important one here. So moving on to dispersion. Dispersion just means that there's a variation in the refractive index with wavelength. And there's two kinds of dispersion. There can be normal dispersion, which is an increase in the refractive index with the frequency, or conversely, a decrease in the wavelength, since they're inversely proportional. And so you can see here in this diagram that this area here and this area here correspond to normal dispersion. So you have this increase in the refractive index with an increase in the frequency. However, you can also have anomalous dispersion, which is just sharp changes in the refractive index, and this is due to absorption of those energies by the material in question. And so here you can see some cases of anomalous dispersion where there's these really sharp changes in the refractive index in a very small frequency range. Now this becomes, so you may think, well, why would you ever want anything to be anomalous? But this becomes important for things like prisms, where you want the material to be highly frequency dependent. Now, moving on to refraction, which is just an abrupt change in the direction of electromagnetic radiation when it passes at an angle through an interface between two transparent media. So if we have an incoming wave here, coming in at some angle from the normal, which is just perpendicular to the surface. Now, when this density of M1 is, I'll say instead, if the density of M2 is greater than M1, so for example, if we're coming from air to water, for example, if this ray of light is coming from air into water, the beam is going to bend towards that normal. Now, the opposite would be true if M1 was in fact more dense than M2. But this extent of refraction, or transmission as it's sometimes called, is given by Snell's law. And this just states that the extent of refraction is governed by the incident angle, as well as the refractive angle, and the refractive indices of the two different media. Now, transmission occurs, but there's something else that always occurs when radiation crosses an interface between media with different refractive indices, and that's reflection. So at the same time, reflection of this beam of light is also occurring, and we know by Snell's law of reflection that this incident angle here is equal to the reflective angle. Or you could say that theta I is equal to theta R. And this is always true. The reflected angle is always equal to the incident angle. Now, some of the light is transmitted, some is refracted, and the proportion of each depends on the refractive indices of the two media as well as the incident angle. Now, the fraction of electromagnetic radiation that is reflected is given by this equation. Where IR is the intensity of the reflected radiation and I naught is the incoming intensity of that radiation, where the intensity is proportional to the magnitude of that electric field of the wave squared. And this is also known as irradiance or photon flux density. But the fraction of reflected light, again, depends on the incident angle theta and the refractive index of the two media. So I'd like to finish off with a question. I'd like you to think about whether the intensity of the reflected light, IR, does it increase or decrease as the incident angle, theta I, approaches 90 degrees?